Please be seated. Hello, this session is getting started. Joe Gordon will speak about Python profiling and performance tuning. Please welcome him with applause.
Thank you. Thank you. So today we're talking about Python profiling and performance tuning. The context for this, I think, is a lot of people have heard Python is slow, don't use Python for large things. Python can be slow at times, but I think hopefully I'll demonstrate you can make Python a lot faster by understanding what's going on under the hood and actually tuning your code. So a little bit about me. I'm a site reliability engineer at Pinterest in San Francisco. This is my first time in Korea, and I'm excited to be here. As a site reliability engineer, we do a few things. We make sure the site is up. So my number one goal is to make sure Pinterest is always available. Also make sure it's performant and efficient, which we'll talk about today. And also make sure to try to increase developer velocity, make it easier for the product developers to make Pinterest better and greater for everybody else. And I'm embedded into the search team, so my goal is actually to make sure search always works at Pinterest. So the problem we had. Back in 2015, the end of 2015, we had this problem where Varnish, in this case, is a reverse proxy that is in front of all our systems. And we had this really slow search subsystem, or search requests were really slow, taking about 2 seconds on the 90th percentile. But what's strange about this is doing a search on the back end on the system the search team actually runs was only about 600 milliseconds or so. So from here, we actually see something really odd, that most of the latency is not from the search team, but from something else. In this case, something else was a huge Python stack on top of it. And so the big question is, why is this happening? Where is this latency coming from? Another interesting note here is that the fluctuation of the latency, on the bottom there is the search system, and on top is Varnish. The fluctuation latency is much larger on the top. So that means there's a huge difference in latency, the peak and the min versus what's happening in the back end. And we also saw the same pattern on all of Pinterest. We had this huge spike. If you went to Pinterest during the day, it would take twice as long as if you went at night. So why? What's going on here? People would just shrug their shoulders and say Python is slow. We have a lot of Python at Pinterest, and nobody really solved it. So to understand what's going on, we have to understand a bit about gEvent. Who here has used gEvent or something like it? Async IO or anything like that? A few people? OK. So gEvent is an async IO like library from a number of years ago. It supports Python 2.7, which is what we use. And it's based on, it's like EventLit and a few other things out there. And it's a coroutine-based Python networking library that uses Greenlit to provide high-level synchronous APIs. What we use it for is we use it for doing, I'll show you in a second, we use it for multiplexing requests on a single process. What's really nice about gEvent is it's a fast event loop. This makes it so you have to do async IO really easily, and also Greenlits are lightweight for execution. This is literally the canonical example of gEvent. I stole it from the website. What we see here is we're actually doing 3 requests at the same time. So we're looking up a DNS lookup, get host by name, on 3 different websites, Google, example.com, and python.org. But instead of doing them all together, all one by one, we do them all at the same time. And so this is what we try to do at Pinterest ourselves, is we have a lot of requests. We have a lot of servers running to handle the requests, and we want to be able to do multiple requests per process per server. So where does gEvent fit in our software stack? This is a very, very, very simplified version of how Pinterest works. The little smiley face is you, the user. If you use the website, you go to the app. Otherwise, you go directly from mobile to the API, and it talks to a whole bunch of different backend systems. When you look a little bit closer to it, you see that we're actually running Python on all the front end. The app and the API are all Python. And each server over there, there's hundreds and hundreds and hundreds of servers running Pinterest. And on each one, we have Nginx, which is another reverse proxy. And behind it, we have multiple processes for Python. We use multiple processes to do multiprocessing because we don't want to use threads due to the nature of the global interpreter lock in Python. And then in each process, we run a different Greenlit for each request. So that way, if a user comes into Pinterest, they get routed to some random host. And on that host, Nginx will actually route them to some random process. And that process will accept the request, spin off into a Greenlit to handle it, and then return. This way, we could actually have a single process doing multiple things at once. So to understand where async IO sort of hits the wall and where it all falls apart, is something called cooperative multitasking. On a kernel scheduler, say the Linux scheduler, you don't actually have to have cooperative multitasking. What happens is a process is running, it's taking a long time, the kernel will interrupt and let something else run. But with cooperative multitasking, you have to yield every time. So in Greenlit, everything runs in all Greenlets run the same OS thread and scheduled cooperatively. This means for a Greenlit to give up control, it has to actually explicitly yield. In the case of G-event, you actually monkey patch all the socket libraries, so every time you do a socket call, you're actually yielding. So this works really great when you have a bunch of network calls. But straight, once again, from the G-event docs, this is not an issue for I/O-bound applications, but it should be something you should be aware when you're doing things that are CPU intensive. So the big question is, what happens if we add CPU intensive work with I/O work? What does it look like? This is actually the nature of a lot of real-world applications. You have incoming requests. Maybe you're doing something that you don't think is CPU intensive, but maybe it is. You're doing some processing, converting from some format to JSON, maybe from XML to JSON or vice versa. You're doing some processing, sending it to a backend service, waiting for the response, and now you have a bunch of CPU and network-bound requests. So to actually try this out, I wrote a little test script. And we have the clients really straightforward, and this is an example of where G-event actually works really well. In this case, I'm using a library called G-request, which is the request library plus G-event. And you could do a bunch of concurrent requests really easily. All you do to have a bunch of concurrent requests is you do this G-request map, and you just wait for every response to finish, and you're done. So it's very simple. It looks like, so these are actually running concurrently, and you specify the number of concurrent requests by passing in size over here. On the server side, we have a simulated server workload. We have a G-event yield, and the yield is there. That's the equivalent of a G-event sleep 0. That's actually just to yield to make things a bit more complicated and to show you what happens to give a more pathological use case. We have a blocking call. This is to simulate CPU-bound work. It could be a whole bunch of things. It could be converting from XML to JSON. It could be processing an image, resizing an image, all kinds of other things you wouldn't expect. Running MD5 hashes is another example of something really expensive people don't realize. Then we have a network call as well, and this is a simulated network call. This is simulated by a G-event sleep. This is to yield. And the idea here is this should take 150 milliseconds in total. You go through the yield, nothing should happen. You do the blocking call, that should be 50 milliseconds, and you do the network call, 100 milliseconds, and then we're done. So you actually run the server, you do 100 calls one at a time, and you get the results you actually expect, right? It takes, on average, 155 milliseconds to handle every request, and the max is 160 milliseconds. That's 10 milliseconds above what we're expecting. There's a bunch of logging in this application, so that's actually not too bad. So that works really well. This is an example of what we expect from our server, right? 150 milliseconds, we see 150 milliseconds. But what happens if we do a bunch of concurrent requests? So far, although the server uses G-event, it actually hasn't been doing anything, multiple greenlets at the same time. So now we do 5 at a time. You see this really strange pattern pop up. A whole bunch of things take 150 milliseconds, about 60%, but a whole bunch take closer to about 250 milliseconds. And some are taking 200 milliseconds. So now we start to see a pattern of what happens when you mix CPU and network-bound work in any sort of eventlet-based, coroutine-based system. So now we go from 150 milliseconds average to 200 milliseconds, and the max is 370 milliseconds, which is way off. And once again, this gets worse and worse as you do more and more requests in the server. At 10 requests at a time, the average is 330 milliseconds. That's twice as slow as what we're expecting the server to be. And the max is half second. And you go further and further. At 15, it gets worse. On average, taking 680 milliseconds to do a 150 millisecond call. And it's up to 1.4 seconds total. So what's going on here? Why is this taking so much time? Why are these requests so much slower than we expect at 150 millisecond goal we're trying to see? So this is an example of the logs we have from our server. And it's a bit hard to read here, but we're looking at request 92 over here. And to simplify it, there's a few things that pop out. So this was from 5 requests at a time. So we enter the G-event yield. The G-event yield, nothing was supposed to happen. It wasn't supposed to take time. But we actually see we're entering a blocking call from another greenlet. And that adds 50 milliseconds over there. We exit that. We go into our blocking call. That takes 50 milliseconds, which is expected. We go into our network call, which would take 100 milliseconds. And we have 2 blocking calls in there, which we could fit. Then we have a third one, which doesn't really belong, and that adds another 50 milliseconds. So in total, we add 100 milliseconds extra from blocking calls. And we take about 250 milliseconds instead of the expected 150 milliseconds. So what this shows us with any sort of coroutine-based system that has cooperative multitasking, you have to make sure how you mix network-bound and CPU-bound work. If you have a lot of coroutines running at the same time, and you have a bunch of CPU-bound work, it could actually slow down the other requests in the other coroutines. So the impact of this was that our system was CPU-bound. Our front-end servers are all bound by CPU. And also, they're also bound by the number of requests we have per process. So an easy solution we had to fix some of this to get a huge win, we actually just increased the number of processes per host. So each host has the same amount of CPU work it's doing, but it's now using more processes in the kernel scheduler will do preemptive multitasking. And so it'll actually interrupt a process, say, hey, you ran for too long, now another thing runs. And that'll actually, this actually reduced our P90 and P99 latency significantly, but there's a lot more we wanted to do beyond that. Another thing is, because everything is CPU bound, we use Amazon at Pinterest, and we auto-scale our front end at 40% CPU. So roughly when you hit 40% CPU usage, we scale up. So that was one of the ways our system works. And one of the nice things about this is it enabled us to have a really simple efficiency metric, which was request per host. So one of the goals in starting this project at Pinterest was our front-end clusters were some of the most expensive clusters we had around. And they also were adding, as I showed you before, they're adding a huge amount of latency into the system across every single endpoint. So the goal was to increase throughput, which, as I said before, we're defining as a request per host, while decreasing latency. And to do this, as we saw with gEvent, the answer is you actually have to decrease CPU usage. We need a way to find all the cases where we have some sort of function that's taking a lot of CPU, but we don't expect it to. So to do that, the first answer for how do you find something that's slow, the answer is you have to measure it, right? So profiling is the answer. We use 3 different profilers to actually get this done. Each one has its pros and cons, and I'll show you the differences. The first we started is a Zig Middleware Profiler. It allows you to generate these really neat graphs. So it's really simple to add on to your WSGI server. It's just a WSGI middleware. In this case, we have it set up to log to my home directory here. And it logs every single request separately, so you can actually see for each request what's happening. The big problem with this is it has a huge overhead, and it can't be used in production. I think it added 20%, maybe 100% latency. It was so slow that it wasn't usable in production, but it was great for running in development environments. The really nice thing about this is you can actually generate, this is what happens, generate call graphs of every single function in a request. This is actually an example. You visit Pinterest.com as a registered user. This is what happens on the back end. This is all the different functions and where the time is being spent. This is a bit hard to read, and actually when I was working on these graphs, I had to print them out in a large format printer to actually read them. So there's a bunch of other ways we try to look at this data. So this middleware we're using actually for the profiling is actually based on cProfile, the standard Python profiler. And you could take the data that's generated by it and pass into this standard library called pstats. So pstats, as you can see here, has some really great features. You can sort by cumulative time, total time, internal time and total time rather. You can do things, you can look at the stats for a specific function. You can look at all the callees and callers of a given function. So here we actually see convert experiment object to dictionary, and you can see that called those 2 functions, and below we can see what called that. So this is a great way, once you find a function that's slow, we can actually walk through the graph and see what gets called by it and what calls it, and try to identify what's slow. Additionally, it has a really, since it's Python, it has a great Python API. So this is a little script I wrote to actually sort out all the slow calls that do not use the network anywhere in there. So in this case, it's really simple logic there. You build the call graph, you get a function, you find all the descendants of that function, anything that's children, grandchildren, etc. And you see if the word socket.py is anywhere in there. If it is, it's a socket-bound function for argument's sake. And this was a really great way for starting out to see, okay, if something's not using the socket, it should be pretty fast. So why are some things that are not using any socket calls actually slow? And it's a bit hard to read on this resolution, unfortunately. But what you actually see here is we had some really strange things. This is 38 milliseconds to check if every user who goes to Pinterest is an employee or not. We don't have that many employees to make this make any sense. We have well under any number that would make 38 milliseconds a reasonable amount of time. So this right here is a great example of one of the things we found right away from profiling is on every request we're spending a lot of time checking if every user is an employee. But unfortunately with this, as I mentioned, this is actually not data from production. This is from a development environment. So the data here is a bit noisy, and it's hard to tell how many requests are, in production actually hit this. Maybe this is some edge cases hit more in development environments. Maybe caching takes care of this in production, things like that. So one of the problems here is still not being able to run in production. But once you have this function, we know that this function here is actually slow, is employee user. They're all pretty slow. We actually want to be able to optimize it. So the first step to optimizing a given function was actually using a line profiler. So we have this call graph. We actually want to see in a given function how slow every line is. So here's an example of a similar function about checking if users are employees. And here's the code here. I don't know who could spot what's slow here. I know I can't. I have, you look at the code, you get a few hunches. Maybe you see here there's a regular expression. Maybe that's slow, maybe not. Regular expressions are notoriously confusing in their performance. But instead of just guessing on what's slow or not, you can actually profile it with every line. And the link to the code's up there. And it's really easy to use. You add a decorator called profile. Instead of using Python, you use this thing called kernprof. And it generates this output data. And then you just parse the output data into this line profiler module. And you get the result here. So you can actually see in this function I'm showing above, there's actually two slow things. One was re.match. And the second one was actually this LDAP list module here, which I don't think any of us expected when we were actually working on this. This is the nice thing about actually being able to profile each line of the code, is you could actually see and find out exactly what's slow and where it is. To generate this data, generally the workflow I've been using is you find the data somehow in production. Maybe it's from a call graph that I showed you before. Maybe it's from something else. And you look up, get some data from production. You generate a synthetic script to run it, in this case, I think 200 times. With a profiler decorator on it and see what's happening. And somebody asked me at work the other day is, why can't you just run the whole thing with this profiler? The answer is that, once again, there's a huge amount of overhead and it's unusable in production. So it's really great for once you found something that's slow, it's great for micro benchmarking. And the answer for this, actually, to fix this code here, we precompiled the regular expression and we dug into the LDAP list logic, and there is a bunch of weird code in there. So once again, both these tools for profiling are really great, and we use them a lot at Pinterest. But the big one we use, I think, the most is a sampling profiler. The problem with those two is you can't use them in production, so we needed a solution that actually works in production. So this is the profiler we use. It's from a company, initially from a company called Nihilus, they're an email company. And I think they're a fully open source email platform. I'm not exactly sure. But they wrote this profiler for their work, and we've adopted it with really great success. And it's a really simple piece of code here. This is actually all 20 or so lines of the code that really matter. The way it works is using Linux signals. So a lot of people have heard of, who here has heard of a Linux signal? SIG-kill, SIG-term? A few? OK, so there's a whole bunch of other signals out there. There's user signals. You can set arbitrary user signals. And there's also alarm signals. So the way this actually works is we register down here. When you call start over here, we set up a timer. We measure the time it started. We add a signal handle over here with signal. So every time a SIG VT alarm goes off, we call sample. And then in sample here, we actually take the frame and we actually store that. And then we set up another signal to actually set a timer, and we call the timer again. So what's happening here is every 5 milliseconds, we're calling a Linux signal, a timer signal, and the Python process with this enabled will actually handle the signal, get the stack of whatever is doing on the CPU, and record that. A few nice things about this is that it's really low overhead. We run into production with no measurable impact on memory usage or CPU. I think the memory usage was a few megabytes over half an hour or so. It's really, really minimal. And then there's another little piece of code here that actually just spawns up a G-event API server that you can actually pull the data from. And the format's really simple here. The format of the data is you have a stack separated by semicolons for each level of stack, and then you have the count number of times it was seen. One of the problems with this data is actually it's a little bit fuzzy. It's every 5 milliseconds. So the way we collect this data is we run it over some arbitrary amount of time, say several minutes, to get a pretty good view of what's going on in the system. And one of the cool things you can actually do with this is you can actually build these call graphs. The call graphs are a bit hard to read. They're called, flame graphs. This was initially, flame graphs came out of Netflix originally, and there's support for them in every language out there now. The way to read this here is the y-axis is the depth of the call stack, and the x-axis is, this is sample data, so this is not a time axis. This is actually the number of times it was seen. So the position on the x-axis isn't important. It's the width of the value on the x-axis that is important here. So we could actually do things like we could zoom in, and you could actually see what some of these values mean. So here we see an example. This function here in code is 6% of the total time that we actually saw. And we know that by its 1,200 samples, out of the, I don't have it here, whatever it was, samples total. And so that's how it's calculated. You take the number of samples you saw that function in, and you divide it by the total number of samples we have, and that's the width of the x-axis. So with this, we could actually see exactly what functions are getting called in production at any given time in any system. Which now you want to ask the question, now we can actually finally answer the question, why is this slow? Where's the time being spent? We could actually go on a production box, enable profiling, and actually see right away. And we actually do this in production. The way we enable this in production is we send this is hooked up to SIG user 2. So this is a user signal. That signal will toggle the profiling on and off. So you turn it on, you wait 10, 15 minutes to collect a good amount of data. So you have a nice amount of data so you get a rich corpus. So you can actually see some of the smaller things, the 0.1% functions and things like that. You collect the data and then you turn off the profiler. And this is how I've been using it in production for quite some time now in a lot of different systems. And it's been really great to actually get a really, really great view on the system. So one of the problems we had with doing this, though, is that you have two call graphs, something changed, your metric, request per host changed, it went down or went up. You want to know what happened. So how do you take two of these and actually look at see what happened and what changed between them? So I wrote some code to a bunch of ways to do this, to actually do a difference of two flame graphs. So here's an example we saw from production. We actually see this filter bad queries was the difference here. So you could actually see you could take two sets of data from 2 different days, say the last week versus this week, and the performance of the system change. You want to see what functions actually caused the change. This will tell it to you pretty quickly. So some examples of how this all fits together, and these are real examples from Pinterest. One of the things we saw actually from using the API profiler was we had this big deep copy over here, and it was taking 30 milliseconds per request. So every single time you're doing a request, you're taking 30 milliseconds to do deep copy. So that looks like a lot, but 30 milliseconds for an end user is really not noticeable. Maybe this is a rare case. So the next thing we wanted to do is we actually wanted to go to production and see, well, what percentage of production traffic, production machines are spending time in deep copy. So you can actually search the flame graphs as well. It turns into an SVG file, which is searchable. And you can actually see from here that 10% of our system was spent doing deep copies on every single server. So this is a huge amount of work is getting wasted on just doing deep copies. And you can actually zoom in on you can't really see it here, but you can zoom in on the flame graphs. And once again, you can actually see, in purple is the highlighted code. And you can actually see what was going on, where the deep copy is getting called from. And from there, you can actually find out who did it. And in this case, the solution was 3 lines of code. The deep copies were there just to be careful. It turns out we didn't have to be that careful about it. The developer writing it didn't realize how dangerous and how expensive deep copies were. So we removed the deep copies. And this is our metric we actually used to track it, request per host. And when we made the change, we rolled the change out of production. We saw this huge spike in efficiency in request per host. So that afterwards, you could actually go back to our flame graphs and actually see, well, it was 10% before. Now we can actually see that after the deploy, that 10% went down to 1.6% in deep copy. So there's a few other deep copies in the system, it looks like, from this, but it's a lot less than 10%. Another problem we had, there's another example. We saw this increase in latency and a drop in efficiency. So latency went up and request per host went down. And once again, these all change automatically because request per host is adjusted by the % CPU usage used. So that number sort of dynamically changes thanks to auto-scaling. So we have 2 flame graphs. Once again, I don't know if anybody can spot the difference here because I know I can't. But you run a diff of the 2 flame graphs. And you can actually see really easily what happened. And here you can actually see it was delta E CIE 2000. In this case, it's some code to generate the difference between two different colors. So there's a bunch of fairly expensive math operations to actually do some color differences. We inform the developer saying, hey, this happened. They go, oh, whoops, we didn't realize that. We're sorry, and they fixed it. And so once again, this is about 2% of the system caused that big change in efficiency and additional latency. Another example we actually saw was serialization. So here's an example. This is zoomed in, but it turns out at one point, we're spending 5% of our time doing serialization to and from a cache system. So it turns out actually we were taking code, we were converting into JSON, and then we were gzipping it to reduce memory footprint. But it turns out converting things in Python to JSON are expensive, and gzipping is also expensive. So by identifying here, we can actually see what was slow, and then we use the line profiler and things like that to actually see which lines are slow. And from there, we realized we didn't need to gzip things, and we actually found out that, believe it or not, pickling is faster than using JSON, which doesn't make sense. This is an example from us recently. Who here has heard of Thrift? OK, for everybody who hasn't heard of it, it's a RPC tool chain to generate language agnostic RPC calls. So at Pinterest, we have a lot of Java, a lot of Python, Go, JavaScript, and a few other languages. And so Thrift allows us to have RPC calls between languages and not have to write all that boilerplate RPC code. The problem we saw in Python, though, is that we're spending 13% of our time doing Thrift serialization, deserialization. So you can zoom in here. We can actually see, here's an example of one function, get users by ID. And you can actually see it's about 4% of the total time. And in there, we have a bunch of Thrift conversion back and forth from the Thrift format to the Python format we're looking for. Thankfully, the standard solution in Python, when something's really slow, you write it in C. So Thrift had a solution for this that came out a number of years ago. That's a fast binary version. And it's a C-accelerated version of the binary protocol we're using for Thrift communication. The problem we had, unfortunately, is Thrift 0.10, which fixes all this, is last I heard not out yet. So at Pinterest, we actually had to backport a bunch of fixes from 0.9.10 to 0.9.3. We had a Thrift fast binary doesn't support Unicode yet, and we support Unicode. It also, see below, there's a big. This is sort of one of the problems of a project that supports 10, 15 different languages. They have strange code. The way they checked if something was fast binaries, they were checking it if something had if the class, so exact matching the class and not anything, not matching any subclasses. And that was the problem we had, is we were using a subclass of fast binary, and it wasn't getting picked up by the previous version of Thrift. We also had to backport a bunch of other changes. I think it was about a half dozen in total. And we deployed it to production, so this huge drop in latency, and we also saw a huge drop in CPU used. And this is that same get users by ID, and it went from 4% to 4 point something to 0.3%. So this huge drop in all these functions here, they're actually taking a long time. And if we didn't actually have any way to profile in production, we would have never noticed that this was such a big thing. We would have just had a suspicion that you look at the code and you say, hey, this is odd, what's going on? But we would have never known how big of an issue it was. And it was hard. Without real data from production, it's really hard to quantify how slow something is. How slow is that deep copy over there? It doesn't matter if it's deep copy if it's called once a second versus something that's called 100 times a second. And you can see the difference here. We can actually look at the before and after once again. And you can see these are a whole bunch in purple. These are all the everything read is Thrift related here. And you can see this is all changes in code that was read calls are not being called anymore. So the impact of all this together was this is where we started at. So latency was at about 2 seconds for search, and the search backend took about 600 milliseconds, where most of the latency was outside of search. And today, the search system takes under 600 seconds. And as you can see here, the really nice thing here is that this is the front end of Pinterest, and this is the search subsystem. The fluctuations in latency are pretty flat. And we can actually see there's only a few hundred milliseconds that are being added by all the layers on top of the search system. So we reduced a significant amount of latency that was incurred by bad Python. So this is, I think, is a bit more telling. This is the site-wide latency. So at the top here in light blue is where we were in Q4 2015, and this is where we are now. We're actually a bit lower than this now. But this was the difference in latency. You can see here the latency curve now is much, much smoother than it used to be, and it's also much, much lower. So this was primarily due to driving down, understanding why our Python code was slow, figuring out what it was, running things in production, profiling in production, and actually identifying the problems. Some conclusions. I think one of the important things, if you're looking at a big Python project that somebody says is slow, maybe we should look into it, is don't guess about where things are slow. Generally, when you guess about performance, you're going to be wrong. First thing is to understand what the bottleneck is. Is it network, CPU, memory? Is it some part of code? Is it cooperative multitasking, some like coroutine system? Once you have a basic understanding of what the bottleneck is, maybe CPU plus cooperative multitasking, profile your system in production. Synthetic benchmarks are never enough. You maybe have a great benchmark, but if you have production data, it's going to change day to day and week to week, and it's really hard to produce synthetic tests that look like production. I think the really important part for us was being able to have visibility into what was slow, made a huge difference. And just guessing, as I said before, it never really worked. Profiling the code really helped, especially in production. Defining efficiency metrics. So if you have this goal to increase efficiency, you need a metric to define. In our case, it was request per host, but there's a whole bunch of other great ways to define that. And the flame graphs I mentioned before, I know this is a Python conference, but they work very well in every other language out there. Java has great support. Node.js has support, and a whole bunch of others. One of the things we found was often fixing the code is much easier than finding what to fix. Generally, it was 2 or 3 lines of code to fix. But finding where the 2 or 3 lines are is a needle in a haystack otherwise if you don't have any profiling. Start with the low-hanging fruit. Any big projects can have lots of low-hanging fruit in performance. And one of the big challenges we're dealing with today, and I think one of the big challenges in general, is actually being able to detect and fix performance regressions as they come up. So once you get efficiency up, it's very easy for a developer to make a mistake about some code and not understand what's going on and commit some code they didn't realize is so impactful on efficiency and performance. And thank you. Any questions?
Thank you for the speaking, Jordan.
Thank you.
If you have a question, you can talk more. Come to the mic if you have a question. Please join Gordon with applause for the presentation.
Thank you.